Hello, everyone, and welcome to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. My name is Alex Alder, and I'm here to help deliver and coordinate the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar, you can email your recommendations to us at ufs.modeling@noaa.gov, and we'll take your suggestions into consideration. Just a few notes about the event. Due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them on the Google document that will be provided in the chat box shortly. Presentations will last about 45 minutes, and then we'll have about 15 minutes Q&A at the end. And again, just type your questions into that Google chat document that we'll be sharing around. Today's webinar is Seasonal Prediction with the Unified Forecast System, presented by Philip Pajian by OAR Physical Science Lab. Mr. Philip Pajian is a physical scientist and Deputy Division Chief for the Modeling and Data Assimilation Division within the Physical Sciences Laboratory at NOAA. He was previously with the University of Colorado Cooperative Institute for Research in Environmental Sciences. Mr. Pajian received his Master of Science in Meteorology from Florida State University in 1999, then worked in the NASA Seasonal to Interannual Prediction Project / Global Modeling and Assimilation Office for over 8 years. Then 1 year at the National Weather Service's Climate Prediction Center before joining the University of Colorado in 2009. His current research focus is on improving numerical weather prediction through advances in atmospheric modeling, data assimilation, and better use of ensembles by better accounting for model uncertainty. He has previously studied the role of SST forcing and atmospheric internal variability in limiting the predictability of seasonal climate, statistical post-processing of seasonal forecasts, initialization of the coupled model for ensemble forecasts, and support the development of MERRA. I'm going to turn it over to Philip, and we'll get going.
All right, well, thank you. Just waiting to share my screen. All right.
Perfect. We can see the screen now.
Okay, just bringing up the slideshow, so hopefully you can see and hear me now. So thank you for the introduction. So yeah, today I'm going to talk about seasonal prediction with the UFS, focus on efforts that we've been doing within the Physical Sciences Lab. I do want to, sorry, acknowledge my co-authors first. Xiaowei Quan and Jonathan Beverly, both with the University of Colorado, who helped carry out these experiments and do the analysis. And also want to say that there is also complementary efforts working on developing the seasonal prediction system at the Global Systems Lab, which is in this Boulder down the hall for me. Also at the NCEP Climate Prediction Center is doing development experimentation there, and also the academic community, specifically George Mason University. So the introduction is that we are in the process of developing a seasonal forecast capability using the UFS framework to replace the aging climate forecast system version 2, or known as the CFSV2. CFSV2 went operational in the spring of 2011, generating an ensemble of 9-month forecasts with a fully coupled model every day. The components of this model consisted of a T126 GFS with 64 levels, with nominally 1 degree atmosphere, with the NOAA land model, a MOM4 ocean, and a 2-layer ice model. That's on nominally a ½ degree grid that does refine to about a ⅓ degree in the tropics. The thing I do want to point out here is that because of the time to do the reforecast and the reanalysis for this, the GFS version they're using as the atmospheric model is from 2007, so it's 17 years old now. So continuing the introduction is that we are in the first year right now of a focused development of the UFS of the SFS, the seasonal forecast system. So last spring, scientists from NCEP, the NOAA Research Labs, and the Developmental Testbed Center, DTC, drafted a development plan outlining the goals of the project and organized a seasonal forecast system application team. So there's a document that we put together that unfortunately is not publicly available right now, but we're hoping to get that out soon. So the target configuration for the seasonal forecast system ultimately would be a half-degree atmosphere, so C192 and FE3 grid speak with 127 levels. And the intention is to have the interactive aerosols, and we're also targeting a 1/4 degree ocean, sea ice, and wave model to go along with this. But we're going to experiment with what's the cost benefit versus loss of adding waves, adding aerosols, etc. And the starting point for this focus development would be that starting with the tagged version of the UFS, which will become the GEFS version 13, or the Global Ensemble Forecast System, which is the coupled system that has a target, excuse me, target timescale of 35 to 45 days, and that version will be run at 1/4 degree. So our baseline would be starting with a 1 degree version of that as we basically start building up this system. So in the meantime, before this project even got started officially, we were already starting to do work, and some of the work was supported through a grant from the Weather Program Office in concert with NCAR. And in that project, we coordinated experiments to compare the impacts of stochastic physics on SS timescales in the NOAA UFS model and then in NCAR's ESM. And as part of that group, part of that project, both groups, so NCAR and PSL, NOAA, generated 50 to 100 year long running free climate simulations that just have basically just internal variability of the model. And in terms of the UFS run, we also had some varying greenhouse gases. And then we did experiments without stochastic physics. And then these simulations were the ones that we did at NOAA. We basically handed the data over to NCAR, and then they ran their climate variability diagnostics package on both sets of experiments, and I will show some of that soon. And then we've done additional diagnostics on the UFS simulations using MDTF, and then some more just one-off plotting too. So this is a result from the CVDP package from NCAR showing just the interannual results of sea surface temperature. That's interannual variability, so the standard deviation across years for the DJF seasonal mean. And I'm going to orient you to these plots. Can you see my cursor?
Yes, we can see the
okay,
cursor.
okay, good. Okay, so I'm just going to orient these figures because there's going to be several slides showing the same things. So the top row is always some observed estimate, and there's two observed estimates here. In this case, it's the same data set, but there's a different time period. The top left is a historical record, so it's about 100 years of data. The right side is just a satellite era, so it's only about 40 years of data, just to basically get a sense of what is the observed on the uncertainty in the observations or variability over different time periods. And then the next row is the UFS simulations, and the bottom row is the NCAR ESM2 simulations. And then there's the two experiments. The left side is the deterministic model, so no stochastic physics active. On the right side is with stochastic physics active. And the thing I want to point out here, and a thing I don't think I mentioned, is that in both of these cases, the model is running at about 1 degree resolution. And the thing I want to point out is in the UFS P8 run here on the left, so we're running prototype 8, which was a development version of GEFS that's a year and a half old now. But the thing I want to point out here is that in the 1 degree configuration, the model is very weak in the variability in the equatorial cold tongue or ENSO variability compared to the observations. The observations are about 1 Kelvin roughly, and then in the UFS it's about 0.6, 0.7 Kelvin, so much weaker. And then we turn on the stochastic physics, the amplitude is increases there, which is a really positive impact, but it's overshooting actually, because I don't have it the number here, but I think the El Nino variability in, if you look at the Nino 3-4 region, which is sort of centered around this orange color, is about, I think, about 1.3, 1.4 degrees, where in observations, I think it's about 0.9. So we're too strong now. Interestingly, is in CESM, their default configuration, the sort of deterministic run, has too strong of an El Nino. And when they add stochastic physics, it makes it weaker. And this actually has been seen in several different experiments where comparing different models, that for some reason that we don't fully understand, stochastic physics seems to improve El Nino from either direction. If you're too strong, too regular, it's going to make it more irregular and weaker. If it's too weak, it'll make it stronger. Just it's a magic bullet, and we don't understand it. But it's nice to see those results are consistent with the UFS. And then moving on to looking at the composite evolution of the El Nino. So what I'm plotting here, again, the figures are in the same orientation. Middle panel is UFS, top panel is observations, bottom panel is the NCAR model. So what I'm showing here is longitude on the x-axis and then time going up on the y-axis, and it's the composite evolution of, on the left is El Nino, and on the right is La Nina. So just like in terms of variability, the prototype 8 deterministic run is too weak. And with stochastic physics, again, it's a little too strong, but it looks pretty good. And the improvement's actually even better in the La Nina. That you can see, look at observations, there's this tendency to have a second year La Nina, which is actually quite common. And we just, previous to this year, we actually came off of a third year La Nina. So these La Ninas tends to persist. And in the UFS prototype 8 run, you actually see with the stochastic physics, you actually see this tendency for a second year La Nina that you don't see in CESM. So I was really excited to see that. Then moving forward, now this is looking at trends, really looking at basically the drift of the model. So top is the observed trend showing the global warming. And this is where things start looking not so good in the UFS run. This is the trend over 50 years. We're using observed greenhouse gases, so we expect there be warming throughout the whole globe over this period, whereas CESM is actually doing a pre-industrial control run, so their greenhouse gases are fixed. So not seeing a trend there is not surprising. But back to the UFS, there's clear drift going on in the Northern Hemisphere. It's actually cooling over these 50 years. And so there's some long-term adjustment that we haven't looked into the cause of this. So this is something that could be concerning, especially if we start doing the longer, if we do like a reanalysis where we have the ocean going with, you know, a sparse observation data set. And then looking at the Pacific Decadal Oscillation, and this is where things start looking really bad for the UFS. So it's not terrible in the deterministic run where you have the warm, so let me just orientate you. So the PDO is defined as the first ELF of the Northern Pacific. So you have this warm sea surface temperatures off the coast of California and Alaska, and then cool sea surface temperatures in the Central Pacific. And in the deterministic run, you actually get this hint of that. You see the warming and the cold. And then what you do is regress this index onto SSTs globally to see how the rest of the world is related to this. And you see, I mean, there's this clear connection to the tropical Pacific. That's in observations. Again, this is a little better in CSM, but when you add the stochastic physics and things are starting to go haywire. And not 100% sure what's going on there. And this is something that we need to look into. And then the same thing on the left is just a repeat of the same plot. On the right is the Atlantic AMO, multi-decadal oscillation, and showing there's similar issues, like basically that, you know, first of all, the AMO is too strong in the Atlantic in both runs, in the UFS runs. And then if you look at the far field relationship, like looking at the Pacific, this looks like just an inverse of the trend. So there's something going on that the PDO, the AMO, and the trend are all drifting off together. It seems like that, and this is something that we need to further investigate. And then looking at now looking at precipitation, so again, it's the same orientation. So on the left side is the DJF seasonal mean, so northern winter. Right is the JJA seasonal mean, so northern summer. And again, the top left is, and the top plots have changed now. The top left is the shorter satellite record period, so we have observations over oceans. The right is the 100-year data set, but it's only stations over land, so it does gives you an incomplete picture. So here, the things I want to point out is, if you look over the northern ITCZ over the Pacific, in the UFS, it's too strong, and stochastic physics. It might be hard to see on the screen, but it actually makes the ITCZ a little more diffuse, so a little more variable. I'm speculating that's more variable in time, not that it's just weaker. So it basically spreads it out a little bit. It's hard to see that here. But overall, it doesn't change the climatology that much. You see a slight improvement again in the summer on the right side too. That's, the model is generally too strong in these convective areas. And that's something that's, just needs further research. But again, this is looking at the bottom plots. It's too strong, but it's actually consistent with other climate models. It's not that the UFS is unique in these issues. So then looking at the variance of precipitation. So this is looking at the year-to-year variability of the winter on the left, summer on the right. And here, I see that, and this is consistent with the 2-week of El Nino in the 1 degree UFS on the left, that's stochastic physics, is that the precipitation variability in this area is too weak. And then on the right side, when you have stochastic physics, you're getting more El Ninos, and then so you get this variability in precipitation over the Nino 4, Nino 3, 4 region, where you're getting in an El Nino, this area warms, the convection follows the warming over to the east. So you're getting that better signal that better matches the observations there. And other pieces that look really good compared to the NCAR models, if you look at the Indian Ocean, is like NCAR is just way too strong here with observations where the variability in UFS is weaker and it's closer to observations, and you see that in both seasons. So in terms of trend variability in these free running runs, the precipitation looks pretty good, and it's hard to see, but actually if you look at the coast of California, British Columbia, the variability actually looks pretty good there too. So you are getting storm track variability, getting tropical variability in this model. And then this is summary diagnostics from CVDP that basically shows what is the correlations between the experiments and the observations, and then the top row is the correlations between the second observation data set. So the shorter period versus the long period are a different source. So in that case, the correlation between each of the observations, except for a couple of exceptions, is better correlated itself than it is with the model. But a certain thing, and then there's a color scale here that red numbers, that there's a higher correlation than the low numbers. The thing I do want to point out is, and again, this is consistent with what I just showed you, is that if you look at the El Nino correlation for the deterministic UFS prototype 8, which is this UFS P8C, the correlation is really, really small. Adding the stochastic physics, the next row, brings it up in line to the CESM model. And then even some other fields, like basically say that this El Nino Hobmolars, which this 0.92 is showing, the time evolution is actually looking really good. So overall, on this right here is the mean score that with the stochastic physics, this model is performing as well as CMIC of the CESM, which has been developed exclusively as a climate model. So this is I think, really exciting that, out of the box, we have a model that's competitive with CESM on a lot of these metrics. And then looking more at shorter time scale and correlate, and basically looking at the internal coherence of the model, what I'm showing here now is I'm no longer going to be showing CESM. This is now just UFS, and then compared to observed estimates. So similar orientation. The left side is the deterministic version of the UFS, the right is the stochastic version. And then below are two observed estimates. The one on the left is ERA5, on the right is on an iMerge satellite-derived precipitation data set. And what I'm showing here is the coherence between precipitation and divergence at 850 pascals. And I will spend a minute here to orientate you if you're not familiar with these. So right in the middle here, this is 0. So this is wave number 0. And then to the right, you get increasing wave numbers. So wave number 10, wave number 20. So there's an eastward moving waves on the right side of the figure. And on the left side, so wave number -10, -20, these are westward moving waves. And then in the y-axis is the frequency of this wave. So you think about it as a phase speed, because you have propagation and this is the time. So basically going from like 1/10 of a cycle per day. Sorry, this is, yeah, so that's the further you go up, the higher frequency that the variability is. So the colors shows the amplitude of the coherence between these two. And then the arrows show the phase. So these arrows that are pointing to the down and right indicate that the divergence leads the precipitation by a eighth of a cycle. And so then I just want to show you, then down here on the bottom left is the ERA5 precipitation coherence with the divergence from ERA5. On the right is the observed precipitation with the ERA5 divergence. So you see when you have the model self-consistent, a very strong coherence, but when you comparing it to an independent precipitation estimate, the coherence drops down some. And the thing I really want to point out is on the bottom here, this red blob down here is the Madden-Julian oscillation. And then this section here going up to the right is the equatorial Kelvin waves. And the thing I want to point out is that with adding the stochastic physics, it doesn't have this clean separation as the iMerge does, but it increases the variability along the Kelvin wave, or the coherence along the Kelvin wave waveguide, and also increases the Madden-Julian oscillation variability. And I also want to point out that it is getting a lot of the structure of the divergence leading, the convergence leading to precipitation appropriately. So this is at the lower levels and things look great. But then if you look at the upper levels, so this is now same plot, but instead of divergence at 200 hectopascals, instead of 850 pascals, we're looking at 200 hectopascals. So this is basically your divergence, a loft, basically where the convection detrains. So then looking at the iMerge specifically, you see this Kelvin wave amplification here. You have higher coherence, and now the arrows are to the right, which shows is that the divergence is leading the convection. And this is where I want to point out that the model is actually not doing this as well. It's got some of it, but it's clearly weaker. It's missing the divergence in this Kelvin wave band. It does have the lower frequencies on the other side of these equatorial Rossby waves, but it is missing, or it's really weaker there. So this is something we need to look into. Is divergence just at the wrong height, or is the model just missing divergence? And this is something that we want to look into, because I think this divergence is an important piece for the teleconnections. Basically, if you're getting equatorial convection, the divergence at the higher levels is basically with the Rossby wave source, and it should be interacting with the jets, and then you have your wave propagation that will affect your longer lead prediction. And then just look at more closely in at the Madden-Julian oscillation piece. So now this is a wave number frequency diagram, so similar to the other one. So you have but it's similar, but it's flipped because the bottom is now period. So 90 days, 30 days, 20 days, and then the y-axis is the wave number. So it's a transpose. The thing I want to point out here is this red blob in the left is observations. So you see the MJO band here. That's roughly 40 to 60 days. And wave numbers 1 to 3 is that in the deterministic UFS, it's very weak, and it's now probably too strong in the stochastic run. It's improved things, but probably overshooting. So, and then this is another thing, and these are all the diagnoses that came out of MDTF, is looking at the northern hemisphere blocking frequency. So here again, the deterministic's on the left, stochastic is on the right. And the black line, there's 2 black lines here. One is a calculation from error interim over 20 years, and then the dashed black line is from the Merrill reanalysis. So they're both reanalysis, and they're pretty close, but there's clearly, exactly how the calculation is done. There's sensitivity to which analysis you do. So it just gives you an uncertainty in the observations for this period. And then for reference, this blue line is CAM5, so the NCAR atmospheric model. That's also the same period, 20 years, and it's 5 ensemble members. So that's why you get this range around the blue dash. So on the left side is this out of the box deterministic UFS, and it shows that the blocking frequency is too strong over the Atlantic region, which is this area on the left at 0 degrees, 30 east, so Atlantic sector, and then the Pacific sector, it's both too strong. And then with the stochastic physics, it's still too strong, but it does nudge it in the right direction. So again, this is something that's a positive result. So then looking, especially this question came up really when I was looking at the ENSO plots, basically how, the 1 degree model is not capturing the ENSO variability with the stochastic physics with the stochastic it is. And this is something that a colleague in our lab, Sean Charlesmark, has advocated and has given presentations that stochastic physics helps a low resolution model behave like a higher resolution model. So we wanted to answer that question. And so what we did is we wanted to run a 50-year run, and it's still going. It's taking forever because it's very expensive. We ran a simulation with prototype 8 deterministic at the 1/4 degree, which is the resolution that the model was developed at. So going from 1 degree to 1/4 degree, and we want to compare how this is with the stochastic physics. So the first thing I was going to look at is the bias, because this came up it was yesterday or 2 days ago. We were in a meeting and we were questioning the impact of stochastic physics on the mean. So what I'm showing here now is this is the sea surface temperature or skin temperature actually bias compared to the Reynolds OI version 2 SST data set. And this is annual mean 50. On the top ones, it's 50-year mean. The bottom one is a 30-year mean compared to climatology. So the 1 degree model, first of all, is much colder than the 1/4 degree model. So clearly there was physics tuning done at the 1/4 degree that when you run it at 1 degree, it's hurting us. I haven't looked into what the cause of this was, but it's probably some physics, microphysics relationship between convection and clouds. But then you see down here is that when you turn on stochastic physics, for some reason, the bias is still cold, but it's less cold. So the stochastic physics is improving the mean bias, but it's still got a long way to go versus the bias of the 1/4 degree is not that bad, actually. I mean, there's a structure there, but that's something that could just be variability of like a PDO and whatnot. And then this is what I was really after, is looking at the El Nino variability in the different ones. So I'll orientate. So now I'm zoomed in over the tropical Pacific, and what I'm plotting here is the interannual standard deviation of the seasonal mean sea surface temperatures or skin temperature. And the top left is the UFS deterministic Top right is with the stochastic physics on. Bottom right is observations, and then the bottom left is the quarter degree on what we just did. So in a gross sense, yes, the 1 degree is behaving more like the quarter degree, that you have a stronger El Nino versus the 1 degree run. But in more respects, it's actually, they're very similar because they're both too strong compared to observations. When you get up to the higher latitudes, like off the Kuroshio extension, things behave differently in the two models. But part of that is not surprising because the ocean dynamics at these higher latitudes is very small scale, and we're not resolving that at the 1 degree. Even quarter degree is just starting to resolve things there. But this definitely supports Prashant's argument that the low resolution model with stochastic physics behaves like the higher resolution model. So now moving on to actual predictions. So I'm just waiting for the slide hasn't updated on my side. It's really weird. Okay, now it's come through. So all that there I was talking about is focused on these long climate simulations, just looking at what does the free running model look like? What is the, what's the biases look like? Is it capturing El Nino? Is it capturing all the internal modes of variability? But now we're actually looking at predictions, and this is basically what our target is. So with doing this, we basically started running reforecast. So we have an initial condition data set called replay, which I'm not going to go into here. But where quickly is we basically just nudge the model to ERA5 in the atmosphere and ORS5 in the ocean. So we have a observed constrained data set that is consistent with our model. So it's easy to start forecasts and you don't have a shock. So we ran 30 years of reforecast every October 1st out to 6 months, and they're 10-member ensembles. And then we have initial condition perturbations in the atmosphere and in the ocean to get our initial ensemble spread, and the stochastic physics is active. So what I'm showing here is just a preliminary plot that they're just looking at the forecast skill of this model. So on the left is, we're calling this early development version of the UFS. I also have called in other cases a proof of concept run. It was just, can we do seasonal prediction with the 1 degree version of the model we have now? And the answer, looking at these plots, is yes, and I'll talk through them quickly. On the left is skill maps of the UFS. On the right is on the reference operational system CFS version 2, its hindcast skill. It's not exactly apple to apples because it's a different period. We're doing 1994 to 2023. They're doing an earlier period. But and then when I talk through the plots, is the top left is the October 1st monthly mean skill, and then it goes down below. It's November, December's monthly mean, January, February, March skill, and the same thing for CFS on the right. And if you look at the longer leads, the skill is comparable. Perhaps more skill in the tropical ENSO region here, where in CFS on the right, it's sort of splitting apart, and you definitely see more skill in the Indian Ocean in the longer leads. In the shorter leads, the UFS is much more skillful, but I think that is not fair because the UFS is initialized October 1st. And so what I'm showing here, October 1st monthly mean, is just a 31-day lead forecast. On the right is CFS, and their initializations are actually done as a lagged it's a lagged ensemble towards the end of September. So you actually have a cycle, I think, a week longer lead there. So you're going to lose that initial predictability in that first week or two. So that's why the first month is much better. So it's not like we solved the month 1 problem. It's just lining up the forecasts ever so slightly is different. So sorry, I hit the wrong button there. But in general, just it's, and like I said, we're running a 1 degree ocean model on the left versus the half degree on the right that defines the quarter degree, and it's comparable in a plot like this, and this is really exciting. And then this was even more exciting. So then we're looking at, so this is looking at skill over lead time. So it's basically really, it's just the correlation of the sea surface temperatures in the central Pacific region here, El Nino region. So, and then this is lead time. So, so 0 is October mean, and then 5 should be February mean. So what I point out here is there's many lines here, and I'm going to talk you through them. The first one is the bottom is the CFS version 2 skill. So this is the 11-year-old model, or even older than that now, and it's the worst performing skill amongst the group here. And right here is the legend showing there is a collection of models from the National Multi-Model Ensemble, and it's different colors. And so there's the Environment Canada produces submits 2 models, the green and the red. The light blue diamond is the NASA model. The dark blue diamond is the GFDL Spira model, which is actually in this metric is the second worst model. And then this orange line here is the UFS run that I just showed in the previous plot. So in that case, this model, as of right now, is beating the pants off of CFS2, and it's beating Spear. And the really exciting thing for me is that there's 2 black lines. So the darker black, the black line with the circles is the skill of the multi-model mean. So it's taking in all of the models that contribute to NME, which is the top ones here, not including the UFS, and averaging those models and then computing the skill beats any individual model. Maybe not in the shortest leads, but once you get past lead 2, it's the best model out there. And then there's this other black line with the X through it that is now swapping out CFS and putting in the UFS. So that even getting rid of the CFS, replacing with the UFS, is even boosting the multi-model ensemble mean. So that's, I think this is a really positive result, showing that we have, we have the ability to basically further improve our ENSO prediction. And then, since we're running ensembles, and we're using stochastic physics, I wanted to look at what is the reliability, what is the spread to error ratio of the model. And so what I have here is I only had 2 models on the left side. So what I'm showing here again, so now this is looking at the same Nino index skill leading from October out through June. So I apologize, it's 9 months, not 6 months. And the solid lines is the root mean squared error of the ensemble mean over the 30 years. Black is the UFS, and then the red is the Spear model. And then these dashed lines is the ensemble spread calculated as the standard deviation across the 10 members in the hindcasts. So the thing that actually surprised me is that with the UFS, with the stochastic physics, the spread isn't any bigger than Sphere. I thought we would be stronger because of the stochastic physics, but it's not. And in both modeling systems, we are basically underspread. So the error on average is higher than the ensemble spread. So we have, it's called basically an overconfident or undispersive system. And then on the right, this is a plot that sort of reinforces what I expected, because looking at this plot here on the left, I see that the RMS error of the UFS is basically the same as Sphere, but the correlation is higher. So I was like, so that means there's a difference in the total variance between the two, and that's shown here on the right, where instead of looking at scale, I'm just looking at the internal variability, so the standard deviation of the Nino 3-4 for the different lead times. And then the blue line is the Reynolds OISST variance, where El Nino variability peaks about 1 degree in this region. The Spear model is too weak in its variability. It's missing some of the variance. And the 2 lines here, red line is the variability of the ensemble mean. The dashed line is the total variance. So I'm taking the standard deviation. So looking at all the ensemble members together, not averaging them. So not surprisingly, the ensemble averaging reduces your variance as you go to longer lead times as the ensemble spread grows. But this is where I was saying that, and this is consistent with the simulations, that the UFS is too strong, so it's too much variance in El Nino, and that would basically result in a stronger RMS error or a larger RMS error even when you have a good correlation. So this is something that we need to work on, is basically reducing the internal variability of the UFS. And for this version of the model, I think it's tunable for the stochastic physics, but it's not clear if that's going to be the case when we go to the quarter degree ocean, because of that run that we did with that stochastic physics shows that the model on its own has too strong of El Nino. So that's an area that we need to pursue. So then looking more at these reforecasts, what I'm showing here is the history of the 30-year reforecast for UFS. So on the bottom axis is the time, so going 1994 through current 2024. And then the monthly El Nino index is on the y-axis. And the blue line is the observation. So again, the Reynolds OISST, which when I made this plot back in December, that's where it ended. So I have last date I have, I think, is November of 2024. And the black lines are the 10-member ensemble from each of the reforecasts that we did over that period. And then the red line is the current, well, at the time it was a forecast, but now we're actually, past DJF. So that's actually retrospective right now, but I didn't have time to update the observations through that. So we don't know how well we did there. But there are, there are successes. Like look here, 1994, we captured the peak of El Nino drop down. 1996, we undershot, we created a pretty big La Nina. It didn't happen. So there are still false negatives. And then here, see in 2003, 2004, the model transitioned from a moderate El Nino, went straight through, crashed through to a strong La Nina. And you see a tendency for this actually 4 years in a row, at least some of the ensemble members. So there are definitely issues going on with initializing and predicting the El Nino's evolution through the spring. And then there's another one I'm going to point out here, it's a really odd one, is the 2023 initialization, where many of the ensemble members look really good. It captures the decaying La Nina and warming up, but then there's one ensemble member that's all the way out here. So I'm not sure what's going on there, but there's clearly some issues with this data set, even though on average it has good skill. And then just looking at spatial maps of what these different events looked like. This is just the ensemble mean prediction, or retrospective prediction for 4 different years. The winter surface temperature anomalies. For the top left is 1998 El Nino, which was one of the biggest ones observed. Then the 2003 El Nino on the right. 2016, which was another big El Nino, and then the most recent one, 2024. And the thing that really sticks out to me, and I don't have observations that go along with this, but the thing that really sticks out to me, and this is actually consistent with what we saw, is that in 2024, it's warm everywhere. There's hardly anywhere in the globe that's cold. So the model is really capturing the global warming signal that you're seeing here. And then looking at precipitation, and in this case, I actually did have observations. So again, this is the same thing where I'm selecting El Nino events, and I selected 2 more in this case. So I have I added 2010 and 2019 here as the 2 more El Nino events. So on the left is the model's retrospective forecast. On the right is the observations. So in general, the model is capturing the varying strengths of the El Ninos. So 1990 is one of the biggest ones you see in observations. You see a strong precipitation signal here, the wet over the Central Pacific, and then you see even see the tendency of the southern storm track over the United States and the West Coast being wet. And I have a zoom in on the next plot, on the next panel of that. You can see 2003 is a little weaker, 2010 is weaker, 16 stronger. So you're getting, it's capturing the varying strength of these things. but it's capturing, but it's missing the structure. So look here, especially 2019, where the precipitation was very centralized over the Western Pacific. You didn't have this extension going east. The model's missing that. And in 2024, which was very interesting, we were watching this all year, is that you were getting the convection out by the date line, but it wasn't going east like you sort of see normally in El Niños. It moves eastward. It was exciting, the ITCC, but it wasn't going east. And the model doesn't really capture that. Although the pattern in 2024 looks very similar to, say, 2016, where you have precipitation more or less everywhere. But the other thing I wanted to point out that I just made this plot this morning, and I captured is like the amplitude over the Pacific Ocean, or the Indian Ocean, is stronger in observations, but you're getting this, you're really capturing the pattern of the Indian Ocean dipole. So you're getting the dry in the central and eastern equatorial Pacific, and then you're getting this wet horseshoe around there. So that, I feel like that was a good success, that the model is, is capturing these other signals that do have strong local impacts. And then just a little more zoomed in over the United States is basically showing, again, this is a shorter period, but showing that the model for the Kents, it is capturing the teleconnection of the wet southeast and for the most part the wet west coast. And in this case, it's 2024 on the right. I just with some preliminary data showing the wetness over the east. That's the signal here is actually a little stronger than we forecasted. But in general, like, I think, as a seasonal prediction goes, this is pretty good. So that was, I think, my last slide. Now just onto the summary. And the summary is that we have a 1 degree version of the UFS with stochastic physics has good internal variability. But both versions of the UFS in these simulations have a strong cooling trend in the Northern Hemisphere that we need to look into. And the UFS is missing the coherence between the precipitation and the upper level divergence. And I didn't show it here, but this is also missing at the higher resolution. So it's not a function of this 1 degree. And then going into the reforecast, that would basically, this shows with the replay, they're outperforming CFS2 and SPEAR and Nino 3-4 prediction. And the current state of the UFS is a really good starting point for developing the seasonal forecast. And like I said earlier, we're going to intend to release the seasonal forecast system development plan soon, and we will be soliciting feedback. And also, I just want to point out that NOAA is organizing 2 upcoming meetings. There's the S2S community meeting this June in Boulder, and there's also going to be a UFS S2S applications workshop on September in College Park, Maryland. So thank you, and I'm happy to take questions.
Thank you. I'm going to change it over to my screen so that way you can all see the questions.
All right.
Should be popping up any second.
Okay, let's see, there's a advertisement. Oh, no, sorry, that's the wrong, sorry, that's the wrong one. Okay. Okay. Okay, so I see the question. So the first question, do you use stochastic physics in all model components? Which method do you use? So in these experiments, I've only used an atmospheric stochastic physics. In the UFS, we're using SPPT, which perturbs the physics tendencies, and SCEB, which estimates the numerical dissipation in the atmospheric model and injects winds out of the resolved scales to make up for that. In the CES MRON, they've only implemented SPPT. They didn't have SCEBs. But the thing is, SCEBs is not very active in the tropics, so that it's more focused on the mid latitudes. We do have ocean stochastic physics available in the UFS. We just, in these experiments, it wasn't turned on. Okay, so in slides 13 for these fields, average 5 north, south. I actually don't know what the latitude band is for that one. I have to ask Maria Gene, it's her plots, but I think 5 south of 5 north does sound right. And how does that, I haven't looked at the northern propagation, so I do not know. That's a good question. And question 3, has the 1 degree model been tuned to able to provide realistic forecasts? No, we I just got the out of the box configuration from GFDL. Has been no tuning at all. CESM is nominally the same resolution. They're both nominally 1 degree models. I don't know if it has refinement in the tropics. I assume it does. It's 5. Could the improvement of the multi-model ensemble be simply removing CFS version 2? Very possible. That's a valid question. We haven't, done that calculation, but that's something we could easily do. Last question, the variability in the higher latitude southern hemisphere is too strong compared to observations. What could be the cause? I have to look at that figure. Where is it? Yeah, I actually don't know because it's the 1 degree model. You would think the variability would be a little too weak. So I don't know if that's a drift. It could be associated with the sea ice model. I do not know. That's a good thing we need to look into. And does the PD on AML improve in the 1/4 degree runs? Haven't looked at yet. That's run is still ongoing, but that's something we want to look at. I don't know if there are any more questions that people want to ask.
We'll give it just another minute here and see if any other questions come through.
Sure. Oh, somebody's typing. No, maybe not.
All right, perfect. Thank you so much,
Okay.
Philip. Thank you for your time today, and glad we could do this. And we'll see everyone at the next webinar. Thank you.
If you have, and anybody else has other questions, feel free to email me. And thank you for your time.
Thank you.
Bye.